Hello, everybody. My name is Behnaz Abdolahi, and I'm a machine learning engineer working at Gen9. Our company is a startup company. We are working on wearable devices, and we are making wearable devices for elderly people. My task here is to use and apply machine learning algorithms on different types of sensors and also motion sensors to hardware that we are developing, so to be able to track people and monitor their daily life. I've been working here since 2015, and we are still working on our project, and we are trying to have it as a product ready probably by this year. So let's just go through our presentation. So I want to talk about the machine learning algorithms and what type of algorithms we can use, how we can use our data sets, what type of data set we really need to work with, and how we need to just analyze our data, what type of algorithms you have to go through, how you want to evaluate your algorithms. So the overview of the machine learning, if we want to just say it mathematically, is we want to estimate the functions f. So if we, which is a functionality from x to y. So if x is the given data that you already collected from the whole environment that you have, from different applications that you already have, and you want to just get the y, which is the output of your functions, so you want to define a function that can estimate from x to y. So here we want to just discuss more that what is the relation between the machine learning and different other concepts that they are in statistics and they are in data science. And so you have, if you want to develop a machine learning algorithm, so you have to go through different types of other development softwares or development algorithms, like using data science, which is so you need to just develop a lot of data engineers algorithms and the softwares and applications, and you have to know a lot about the statistics, and also you need to know a lot about the mathematics that is behind the machine learning, and finally you need to know just developing your codes in different languages, which is more comfortable for you. So Python right now is one of the famous one with a lot of libraries that is available in machine learning. There is a big questions that everybody is asking, that what is the difference between machine learning and statistics? Some people think that maybe there's not a big difference if you mathematically consider them. But the general answer to this question is that the statistics are, for statistical actually algorithms, we are assuming a distribution of the data. So, but for the machine learning, we don't assume anything. So we are not dependent to the sampling of our data if we are using the machine learning algorithms. So this is one of the big differences. But if you want to go through that, you can read a lot of articles about that, and then you can just learn more about the mathematics background of between these two types of algorithms. In general, the machine learning algorithms are mainly categorized into three different categorization. One of them is supervised learning, which we have some data and we know the label of our data. Let's say we have a lot of data from different people with a specific type of disease. So we know that each person with different features and with different with different features that we value from measures from these people. So we know that what type of disease they already have. So we call this as a supervised learning. With the unsupervised learning, we have no information about what is the label of our data. So we have feature space, and we really want to just find the similarity of our data and make sure that those people that are really similar to each other, how we can just categorize that into one specific category or class. Another part, different types of algorithms, which is mostly used, especially in these days are semi-supervised learnings. These types of learnings are using both the supervised and unsupervised learning. So they both use some labels data, and they used some unlabeled data that we don't have the labels, and they try to just label those data that they think are really valuable for the whole system to just make the model, improve their models. So active learnings are one of those types of algorithms. So why we need semi-supervised? Because most of the time, having a supervised learning is very, very hard for us to get. It's very time consuming, and sometimes it's impossible for us to just have a different types of labeled data. So we really need to just use semi-supervised learning in some domains. So it really depends on what type of applications you are going to write and what type of problems you are going to solve. So the important thing on the machine learnings are the data sets. So we have to know what type of data set we are working. And also you need to have a background knowledge about the specific domain that you are working. For example, in our company, we are working with different types of sensors. So we need to have a background at what is the behavior of these sensors, and also we have to know a lot of backgrounds about the signal processing. So so if you are, for example, working in a finance domain, then you need to have a lot of knowledge about the finance, so that then you can just have an idea that what is your data is look like and why your data is like that. There are two main repositories that if you want to do a research, or if you want just to work on a data set, and you can just communicate with other people and professionals in these domains. One of them is the UCI repository, which is mostly used for publishing papers. So these repositories are, these data sets are also available. You can see a lot of papers that they mentioned that they just they develop their algorithms, and then they evaluate their algorithms based on different data sets that is available in the UCI repository, which is so it depends on what purpose you are looking for, but you can just go through this website. Another important website is Kaggle. There are a lot of different types of data from even some companies. They put their data in the Kaggle, and they want people to solve their problems, so they can analyze their data. So, and then you can just even if you are in a competition, and if you win the competition, they just they can give you the money. So that's a good thing if you like. So you can go to the Kaggle. Data sets. So what we have when we are talking about data, we're talking about three different types of data that is available in the internet and is available in our world. Some of them are structured data, some of them are unstructured, and some of them are semi-structured. So some data like Twitter data, they are all unstructured data, because if you look at the Twitter data, it's you need to do a lot of pre-processing to be able to just and cleaning the data to be able to just make it ready for your own purpose, to be able to just develop and apply your algorithms on that. So there are different types of parsers that is available that you can just read the Twitter data, or you can write your own parsers. And there are some other data which is called semi-structured data, which is a combination of structured data and unstructured data. For example, the emails, addresses. So you can have a database of people, which is structured data, and then this email, the value of this email, I mean the content of these emails are unstructured data. So you have a combination of unstructured and structured data. So you need to write your own code to do data cleanings and data engineering. You have to just visualize your data sometimes, because your data is so big. Sometimes it's so hard to do that. Then you have to learn a lot of different tools, and then how you can just have an idea of what your data is look like. So that's why most of the data engineers are working on, but that's one of the basic maybe basic part of your project that when you start machine learning, then you have to use these types of algorithms to just clean your data and pre-processing your data to make it ready for your purpose of actually project. Today I want to just go through a data set which is has is very simple database data set, and you can just download it from the UCI repository, and it has 4 features, which is the sepal length of each flowers of 3 different flowers, and the petal length and the petal width and the sepal width. All of them are in centimeters, and for we want to know which type of iris are these flowers. So this data set has, for each classes, we have 50 instances. So we want to be able to classify them. So I want to go through different algorithms at first to show you that what is the difference between them. And then we want to apply some of those algorithms on these data sets, and I want to show you that how you can do that and what is the difference between the accuracy level of different algorithms, and why is this happening for different types of machine learning algorithms that you're applying on that. So let's start with this one. So we have our data sets, as we call. So we have 50 instances. So I want you to just have it until the end of the have it in your mind until the end of the presentation. So we have 50 instances of our each class. So at first, because I cannot show the 4-dimension, visualize that. So I just showed 2 different features. One of them is the sepal length. The left one is sepal length with the sepal width versus the sepal width, which you can see the blue points are one of the classes, the green points are in other classes, and some red points you can see that is another classes. The green points and the red points are very, very integrated to each other, so it's hard to discriminate between that. You can see on the right figures that I just visualize 2 other different features, which is the petal width and the petal length. And then you can see that the blue ones is totally separable from the other classes, and the green one, which is another class, is in the middle, and also the red one, which is on top, is another class. So the green and the red ones are integrated to each other, but so you can see based on 2 features, then you can classify better. So in order to find what is the best combination of features, and for you to be able to classify, this is one part of your data engineers and data processing that you have to work on, and you have to just struggle with that. So in general, if I want to tell you about machine learning algorithms, you can see a huge number of them, but the very famous ones are decision trees, and then you can hear a lot about them because they try to make a tree of the whole features that you have already extracted from your database, and then it tries to just find a tree. So for each tree, the root of the tree is the features that gives you the most important information of the whole data. So you can extract several rules based on this decision tree. So if you have millions of features from a data set, then you can have a very big tree, and then you can extract different rules from the decision trees. So we don't want to go through the decision trees today, but I will just give you more references if you are interested to learn more about it. Naïve Bayes is one of the basic that I want to go through the theory part of the Naïve Bayes, because I want to show that the other types of classifiers are really integrated and are really dependent to the Naïve Bayes. So if you learn Naïve Bayes and the mathematics behind that, then you will learn the other classifiers much maybe easier. So when you hear about the naive Bayes and also the classifiers, then you will hear about different estimations. Each one of them is the map estimations, and the other one is maximum likelihood estimations. We will go through all of them, and then you will hear about the Bayes rule, and then you will hear about the conditional dependency. So that's one of the conditions that if you want to apply naive Bayes, you really want to make sure that your data is conditional independent. Then we want to show that what is the difference between Gaussian naive Bayes and naive Bayes. So in general, the Gaussian naive Bayes are those probability estimation of your data, which is Gaussian. So you assume that the probability of your data is Gaussian. Then I want to try and show you what is logistic regression and what is the linear regression, and also expectation maximization is another algorithms that probably we cannot go through that, but I want you to just know that it's very important to just learn about it. And then we will go through the artificial intelligence and support vector machines, and how the kernel function is going to help the support vector machine, and how it's going to change that, and also the principal component analysis, which is another, which is a very popular data, reduced data representations, which I will show you that how it's going to help us to develop our machine learning algorithms. And then finally, I want to talk a little about deep leaf networks, which is a basic of deep learning. Naive Bayes. The naive Bayes was at first developed, I mean, it was just an idea which was which backs to, which backs to maybe decades ago. No, it's, I mean, Thomas Bayes, he was a mathematician years back, and then this is you can see that the functions that he has written is like this. So if we have a probability of our theta, which is given our data. So theta, I mean, if you have a class, so let's say in our example, for the iris, so we have 3 classes. So we want the theta is our classes, and the data is the information that we are having for different lengths of petal and sepal. So so we want to estimate, and we want to get that what is the probability of theta given our data. So this is how we can rewrite the equation. So it's going to be P of theta multiplied to P of probability of theta given theta over the probability of theta. So probability of theta given theta is called a posterior, and the probability of theta is called prior, and the probability of theta given theta is called likelihood. So the Bayes rule can be written like these equations that are written. So you can and also you can rewrite it because of the conditional independency. So the probability of the whole the summation of the denominator can be written as the rewrite as the multiplication of the probability of each class, which is P of y equal to yj. So if this is the probability of class 1, then you can multiply that with the probability of xy given y. So it's the probability of our data given the class labels. So if we have a summation of all of them, then that would be our denominator. So we can rewrite that as like this. I mean, we can rewrite the first equation as like this because we have the conditional dependency. So that is the whole equations that we want to go through, and how we can use that to classify our data. So we talk about the maximum likelihood estimation. So if we want to solve this problem and estimate these functions and this probability, then we can use maximum likelihood estimation. So if we try to find the maximum of the P of probability of data given our theta, then we can just solve our problem. So if we try to maximize that, then based on that, then we can just we can just say that the probability of theta given data is going to be solved because we are if we just use this estimation, then we are estimating for our purpose and for our own functions. So let's say to be a little more clear, let's say, for example, you want for our different types of flowers that we talked about. So our theta, which is the parameters of the prior data that we have from different flowers and different data that we have. So we know how many number of type 1, how many number of type 2, and how many number of type 3 we have. So we can just estimate our prior data, and then based on that, we can just find the probability of then we can just use Naïve Bayes to be able to find the probability of data given theta. Another one is maximal posterior, which is exactly if we want to give our prior data, we can just define it in another way. So our prior data is going to be plus another estimation. So in another language, I can tell you that if we want to find a probability of theta given data, instead of just finding the probability of data given theta, we can just estimate the probability of the whole numerator. So we can just estimate the probability of theta multiplied with the probability of data given theta. So this is the difference between the posterior map and also maximum likelihood. For the maximum likelihood, we just estimate the probability of data given theta. So we can go through, we don't want to go through that, but if you're interested, then you can learn more about that, which is the beta estimation, beta distributions, because we are using beta as our period data that we are adding to the whole estimation of the parameters. Logistic regressions. Logistic regression is one of the algorithms that machine learning algorithm that is that is a supervised learning, and it's based on the mathematics. You can just drive logistic regression from Naïve Bayes. So that's why learning the Naïve Bayes is very important. So we want to just learn again the functions, which is P of y given x. So if y is the label of our classes and x is the data that we already have, then we based on the Naïve Bayes, we always compute the other side of our equations, which is P of x given y and also P of y. But the logistic regressions tries to estimate the data from the probability of y given x. So why not use that? There are again a lot of theory in back. So for example, we can assume that the probability of y given x as a distribution of Gaussians, and then let's say the probability of the y equals to 1, which is one of our classes given x. If we only have 2 classes, then this probability could be written as these equations. So we can prove for that, which is not so hard. And this is sigmoid functions. So if you want to see that what is this function look like, is like we call it sigmoid function, which is like that. So this is the difference between the logistic regression and Naïve Bayes. Now I want to talk about neural networks. Neural networks are another types of machine learning algorithms that they try to simulate how the brain is working. So they try to find the estimate our functions based on different neurons. So they will have different layers, and we are trying to have our data as an input layers, and then we will have maybe one or more than one hidden layers in middle, and then the output layer is going to be our data that we are looking for, the labels of our data. So each unit input again has a sigmoid function as we showed before, like the sigmoid function that we defined for the logistic regressions. For defining the neural network and for solving the neural network and finding the whole different types of weights and learn the weights, then we can use the MLE and also map estimations, which is we just discussed that before in Naïve Bayes. So these are other equations that if you like, you can go through that, which is not so hard. And then you can understand that how for your own data that you already have, then you can find these probabilities, and then you can define your each weights for each iteration. So finally, you can learn the whole weights of your of the model, and then you can use that in future. So let's say if you have a database of different images of different peoples, so you will try to just use them as an input to your neural networks, and then this neural networks is going to learn different weights, and then finally these weights are going to be used for new instances that we don't have any information about them, and then we can just predict that what is this person, is this new image is going to be look like who is in our data, I mean who another person that is which is in our database or not. And also the people are going to just wear different, for example, they are going to change their hairstyle, or even they just wear glasses or not wearing glasses. So neural network can handle these types of changes. Another example, which is very popular example, I wanted you to look into that, because these days is autonomous driving is very, very, you can read a lot about them, and you can see that this project was developed in 1993 and in CMU, and they try to just use neural networks with different images, and they try to just use a car to give the directions to the car, so the car can just turn right or left. I copied this slide from Tom Michel's at CMU. So if you want, you can go through that, and then I will just put the links that you can just have more information about this project, and also you can go through the papers too, which is very interesting because it works very good in that time. Support vector machines. This is another type of machine learning algorithms, and they really want to find a decision boundary for the data that you already have when the data is linearly separable. So why we need support vector machines, and why Naïve Bayes or the other algorithms that we have talked are not going to work sometimes for us. The reason is that because sometimes only the boundaries of your data between the different classes are important for you. So if you try to have enough information about that, then you can develop your classifiers. So if, let's say, we have a data like this, so we have a lot of positives and negatives samples, and then we want to, and we know that these data are linearly separable, then we need to just define a functions which is aligned, then we can discriminate between these two classes. But the question is that which line is going to be the better line, which one we have to choose. So support vector machines try to use different, another approach, which is called support vectors. So it tries to find the best line for us. So but in another way. So each line tries to find the vectors which are support vectors, which are those instances that are pretty near to the lines. So we try to minimize the distance between those support vectors to the lines, and we try to just maximize the margins between these two lines, and this area that is the separation between these two classes. So we try to maximize, here we call it gamma, then we try to maximize the gamma, and also we try to minimize the distance between each support vectors and the lines. So by this way, we are just have another objective functions, and then we just classify in another way. One important question will be that if our data in our input space is not separable, so like the image on your left that you can see, so the data is not separable. The red dots cannot be separated linearly from the blue dots. So there's another version of support vector machines which they call it kernalized. So they use the functions which we call it kernel. So you can map these input data to another space. So in that space, you can, which is which is a higher dimension space. So in that space, you can just define a linear functions. And one of the most popular one and commonly used is the Gaussians. But there are, especially years back, there were a lot of papers that you can find that people are having their own data sets, and they try to show you the best kernel functions that in that space their data is separable. Before I want to just talk a little about deep belief network and deep learning. But before that, I want to show that what is the reduced data representations, which is a very commonly and very important concept in machine learning. So we have a concept which we call principal component analysis. So let's say if we have a data set at the left side, we have a data set of our features. So if we have our iris database, which is a sepal width and a sepal length, and you can see that these data are not separable. So if we just use another representation of our data, which we call it principal component analysis, you can see, and then we use only the three largest component of our PCA, then you can see on the right side, these three classes are separable. So this is another data representation that we can just reuse our data, and then we can just represent our data in another way. So deep belief networks is have an idea, something like that. So this is, I copied this from a famous paper which was published by Hinton, and it was the basic of deep learning. So you can see that they try to have an encoder, and then they decode their data, and then they just reconstruct the image that they already have. So they put a lot of images to this encoder, decoder, and then these layers of learning, they just show that we can reconstruct again the image. So this is going to help to represent our data in another way. So this is, they try to just show the difference between PCA that we called before, and also we apply that on our iris database, and also the deep belief network. You can see that, for example, the green points are the data of the images from the same person. So those people that are greens are totally near to each other, or the images that are purples are from the same person, so they are near to each other. But you can see on the other PCA, then they are not near to each other. It's hard to separate them. This is just the encoder and autoencoder. The encoder decoder. This is just the basic actual idea of the deep learning. But we don't want to go through that. But if you want, I will just put more links, and then you can go through the papers and the links through that. Generative and discriminative classifiers. All of the classifiers that we discussed so far, some of them are called generative and some of them are called discriminative classifiers. The generative classifiers are those like Naïve Bayes that we have a distribution of our data, and then we can generate more samples from that. That's why we call it generative methods. But the discriminative methods are those that like logistic regression. So they are directly estimate the probability of y given x, and they just assume a functions for this p of y given x. This is so I wanted to know that if you hear something about the generative and discriminative classifier, then you know what is the difference between them. This is another categorization of classifications techniques. Evaluation metrics, which is very important. When you have a classifier, then you need to just show how good is your classifier working. So important thing is that, let's say in this example, which I again copied from Andrew class, machine learning class, it shows that if we have three different, if we have the same number of points, which is the size of the bedrooms based on the price of the house, then if you want to estimate with different hypotheses that it mentioned, or different functions that it mentions here, then the left side, you see that these functions is high biased. It means that the estimation is not very good. The the most right one is define a function, which is very complicated, and it has a higher order functions, but you see that is high variance because it's overfit your data. So in future, if you have another instance, then you will have a high error if you want to estimate what is the price of this house. But the middle one is the best one. So there are different types of techniques that we want to avoid overfitting, and we will just use regularization terms. So so after you use different estimators like MAP or MLE, then you need to just make sure that how biased and how much variance is your estimator, and then you can just based on that, then you can just make sure that how good is your estimation, or do you have to change that or not. So this is another question. If you like, then you can think about it, that if you have a coin which is fair, and if you haven't used MLE as an estimator to find the probability of your heads, then can you estimate that the MLE is going to be biased or unbiased? You can think about it, but if you want, then we can just discuss the answer to these questions. Talk about overfitting, that we should avoid overfitting in our data, because if we have a very, very accurate functions which is working on our training data, then our test data, then maybe it's a lot of work and we will have a high errors. Then there are some mathematics regularization terms that you can add to your whole functions and estimations, and then you can define better functions with lower error for your test data. There are other concepts like precisions, recalls, F1 scores. So I guess we don't have a lot of time because I want to go through the iris data sets and show what is this, what is the evaluations and how we apply the machine learning techniques. But the precisions, just a brief review is that if you have, let's say, 2 classes, and if you know that the prediction of each class is going to be only yes or no, you don't have any other values for this class. So if the actual value of this class is going to be yes, and also you predicted yes, then we call it true positive. If the actual value is no, but you predicted yes, then we call it false positive. If the actual value of the class is yes, but you predict the class as no, then we have false negative. And also if your just actual class is no, but your predicted class is no, then you have true negatives. So these are important evaluation metrics that you can just design that, and then you can measure them for each classifier that you have. And ROC curve is another one, so you can read more about it. But I want to go through the precision, recall, and F1 scores, so we will calculate that for our database. So if this is our iris data set, and I told you then we have 50 number of instances for each classes, and we want to classify that. So we read the data as we discussed that. So these are, I just show different features that I plot different features that you have an idea that how your data is look like. So what type of machine learning algorithm is going to be best for you to use that. So this visualization maybe help you to give you a better data of your better visualization of your data sets. So I talked to you about the reduced data representation. Then maybe if you think that your original feature space is not good enough, then you can use the reduced representation of data. Then, so I want to show that what is the difference between Gaussian, Naïve Bayes, logistic regression, neural network, and SVM on this data set. So the result that I got, I developed that in IPython, so I will provide the code. So if you want to play with that with different parameters, then you can do that. So the Naïve Bayes for the F1 score is the accuracy level is 0.96, and I calculate the confusion matrix too. So if you want, you can have an idea that how many number of the whole data, how many number of the instances are just predicted wrong. And the the neural networks gives us 0.96 accuracy level, and the SVM, it gives us 0.97, and the logistic regression gives us 0.98. So the comparison result shows that the logistic regression is giving, for this data set, is going to be the best. So so in this presentation, I wanted to just show you that how you can develop that. And right now you can see that with different, with one database, you can get different results based on different types of machine learning algorithms that you are using. But the question is that which one is going to give you the best, and how you make sure that this logistic regression is not overfitted. So you have to make sure if it's overfitted, then maybe if you use other types of data in future, I mean the same data, but other data that you haven't seen before, then how accurate this is going to just predict the results. And you can see for this database, neural network is not good, but for other database like image analysis and face recognition, then you can see neural network maybe is the perfect one. So it really depends what type of data do you have and how you want to evaluate them, and then you can find the best machine learning algorithms. So let's go through the questions. Link to the slides. So a person asked link to the slides. I guess yeah, we'll replay them later. So I will give the slides and also the links to the papers, and also the links to the code that I've written to develop this iris this iris database. Then if you want, then you can work with that. Oh, a person mentioned I need to study your talk in full, I think, but it's been very thorough. Oh, okay. Yeah, I tried to, I wanted to just go through more deep inside the mathematics of machine learning, which is not very hard, but maybe it helps people a lot to understand that what's happening exactly, not just applying different algorithms, because there are several libraries available right now that you can just use them and you can just apply them on your data sets. But if you learn how this is the background of them, then you'll just have better idea of what's happening. And then if you have different data sets, then you have an estimation which algorithm is going to work best and why it's not working and why you have to do it the next step. Do you have to change your functions, or do you have to change your features? Do you need more data? These are other things that I didn't have enough time to talk about, but sometimes you have to make sure maybe more data is going to help you, but maybe sometimes more samples is not going to help, but you need to change your features. Okay, questions. In which case Bayes is better than logistic regressions in terms of data structures? Okay, that's a very good question. If you work with data, I can tell you, if your data is so nonlinear, I mean your decision surface is so nonlinear, then Bayesian is going to work better for you. But it's hard to say that which one is going to be better, logistic regressions or Bayesians or naive Bayes. But we can discuss that more. And I mean, if you want, I can give you more links to that they discuss more completely about it. But the issue with the naive Bayes is that you always have the conditional independency assumptions. That's not very good all the time. Maybe sometimes your data are not conditional independent. So in that way, logistic regression is going to work better for you than naive Bayes. So that's one thing, that logistic regression is better. Although if you go through the theory and the proof of logistic regressions is using naive Bayes. So at the first, in the proof, the conditional independency is an assumption, but as I told you, we just use the probability of x given of the theta given data. So we are using the original probability for estimation of the logistic regression. So the conditional independency is the important issue with the naive Bayes. So sometimes maybe logistic regression is better. Okay, thank you very much, everybody. Have a great weekend. Bye.